Hello, my name is Marcella Chilia and I am a geologist with the U.S. Geological Survey Earthquake Science Center in Menlo Park, California. So today I am very pleased to be talking with you about the origin of the 2018 Palu tsunami. So we will firstly briefly discuss the regional setting, then go straight into why Palu is such a unique event, talk a bit about how the literature around the tsunami origin has evolved and some of the proposed mechanisms, and then we will look at one very comprehensive model in particular, and then wrap up with a summary and lessons learned from the Palu tsunami. Okay, so what we can see on this seismicity map of Indonesia is that clearly Indonesia has very high levels of active seismicity. But for this talk, of course, we are just going to be focusing on Palu city, which is shown here on the green dot. And this is located on the island of Sulawesi. Now, Sulawesi is located in a convergent zone between three major plates: the Sunda plate, the Pacific collision with the Philippine Sea, and the Australian plates. And together this forms a rather complex pattern of plate boundaries with active subduction, shown with the black-filled triangles, and collision zones, particularly towards northeast Sulawesi. But also there are some rather prominent strike slip zones further south and towards the central parts of Sulawesi Island. And the red box here is our study area. And as you can see, there is a major fault running through it. This is known as the Palu-Koro fault, which passes directly through the west of Palu city. So if we look over the past 20 years or so, we can see that actually there have been very few tsunamigenic earthquakes, or in particular, megathrust earthquakes that have generated a tsunami. And for this magnitude 7.4 Minahasa event in 2018, there was a tsunami warning that was issued, but then was later cancelled. Now, if we compare this to the amount of crustal seismicity, we can see there are many more events here. And most notably, we can probably quite easily identify the September 28th magnitude 7.5 Palu event, which is here. Okay, so why is the Palu tsunami such a unique event, and why has there been so much attention and debate around it? Well, firstly, the Palu earthquake actually occurred onshore, and here's the focal mechanism, onshore on a left lateral strike slip fault. And tsunamis are usually generated by subduction zone thrust faults that uplift the sea floor. Yet, the Palu earthquake generated multiple tsunamis that caused severe damage within Palu Bay and also up the east and west coasts. And so here we have the mystery of a non-tsunamigenic mechanism. And further to this point, if we take a look at a slip model, here we are just using Lee et al., published earlier this year, we can see that the slip distribution has been split into 4 different asperities. We can see some relatively low slip of about 3 meters at the epicenter, but as we go just over 50 kilometers south, we can see that the slip more than doubles as the earthquake hits Palu Bay and into Palu Basin. And this slip model is consistent with many other models too. So the big question that was proposed in the science community is, whether the tsunami was mainly triggered by co-seismic deformation or by shaking-induced landsliding. And there have been many studies published to try and answer this question and essentially identify the tsunami source mechanisms. And what the research actually shows is the answer to the question is a complex combination of both of these factors. Okay, so now we're just going to look at a couple of proposed tsunami source mechanisms, the first of which is landslides, both coastal and submarine landslides. So here we can see a conceptual diagram of tsunami waves generated by landslide movement. So figure A shows pre-failure, so everything is normal. And then figure B shows initial slip, which with surface drag down above the rear of the submarine landslide, and this has generated positive and negative waves. And then finally, figure C shows continued submarine landslides, movement and wave propagation further south down Sulawesi Neck. Now the second part of the story, and also the second proposed tsunami source mechanism, is the fault displacement. So here we can see a schematic model of the west and the east block in the Palu Coral Fault, which is based on a hypocenter relocation. So interestingly, this shows that the fault plane interface is deeper into Donggala and follows the Makassar Strait bathymetry. So an interesting proposition here is whether a fault displacement in the deeper northward segment towards the epicenter, which is the red star here, could have triggered enough change in the seafloor bathymetry to generate a tsunami. Okay, so here we can see a timeline of how the literature has evolved and generally how the understanding has improved or changed related to the origin of the Palu tsunami. So the studies in black were field studies that were conducted, so direct measurements of inundation, run-up heights, etc. And in red are the studies that computed a tsunami model, and these vary in complexity. But for this particular talk, we are just going to be focusing on one rather comprehensive model published earlier this year by Sepulveda et al. Now, when we consider tsunami models, these often rely on two important concepts. That's optical imagery and finite fault models. So we're just going to briefly talk about both of these concepts. Okay, so the concept of optical imagery is that satellites with optical sensors are used to generate images of the Earth over large areas and distinguish changes in landscapes. So these sensors function in the optical part of the wavelength spectrum, and this includes visible, near-infrared, and shortwave infrared wavelengths. And we can see a simplified summary of this in figure A. And so the second concept when looking at tsunami modeling is finite fault models. So a finite fault model is a modeled representation of the spatial extent, amplitude, and duration of fault rupture or slip of an earthquake. And this is generated via the inversion of teleseismic body waveforms and long period surface waves. So let's take a closer look at the Sepulveda 2020 model. So here we can just see a regional map of Sulawesi with the major plate boundary faults of the Sula block. And then in Figure B, we can see some of the historical events associated with tsunamis in the last century, which is indicated by a star with the year as well. And if you take a closer look at Figure C, then this is a zoomed in map of Palu Bay. Now we can see that there are 4 different fault geometries that are proposed in this study, and their corresponding fault traces are shown in the different colors. So magenta, orange, red, and green. So model 1, which is a magenta, has a straight line fault trace beneath the bay, connecting the fault trace observed at Palu City to a point close to Pantoloan, which is here. And then model 2, which is the orange, assumes the same geometry on land as model 1, but follows the Palu Koru fault along the coast and then makes a restraining bend in the middle of the bay, as you can see here, and then goes back on land. Model 3, which is in red, follows the main geologic trace of the Palu Koru fault, like this. And then it actually jumps to the observed northeastern fault trace. And model 4, which is in green, here, this assumes a fault approximately aligned with the trough in the bathymetry along the central axis of the bay. So there are 3 main types of data that have been used in this study, and these are INSAR, which stands for Interferometric Synthetic Aperture Radar. And this is an effective way to measure changes in land surface altitude. Also, tide gauge data were used, and only 2 are available for this particular Palu event, as well as video-derived time histories from social media. So with this data, a total of 12 static slip models of the 2018 Sulawesi earthquake have been created using these 4 different assumed fault trace geometries that we saw just a couple of slides ago. So the dip angles associated with each fault trace model vary here between 70 degrees, 80 degrees, and 89 degrees. So the color indicates the total slip magnitude, and the magenta arrows actually show they indicate the rake. And then we can also see the RMS, the root mean square errors of each inversion shown in the headers here. So in this case, the geometry of model 1 with a straight line fault trace beneath the bay shows high slip just south of Palu Bay, and is actually similar to what has been proposed by Socket et al. In 2019, as well as the USGS model. Now, model 2 is associated with a pretty strong dip slip component of about 3 meters at the hypothetical fault bend, which we saw earlier as well, which gives a larger tsunamigenic potential. And among all of these models analyzed, model 2, the model 2 with 70 degrees dip in particular is associated with the largest co-seismic distribution to the tsunami generation. Model 3 has one segment following the main Palu fault along the west side of the bay, which was also found in Watkinson and Hall's study in 2017. And since there are no direct signs of a fault trace in the bay bathymetry, this geometry would appear to be equally likely as Model 2. And we can also see slip a bit further south and not as high in some regions to the north. For Model 4, there are no specific observations to support this other than the large-scale bathymetry, and it's included in order to represent an intermediate value of the fault plane strike. So for this study, there were also simulated run-up heights from the Palu tsunami. But first we must know what field observations are used, which will be then compared to later. And in this case, there are data used from 3 different field studies, as you can see here. And the maximum run-up height recorded in these studies was up to 10 meters. So these are the results from the simulated tsunami run-up heights. Overall, none of the simulated run-up heights from the 12 models can explain the observed values, which exceed 10 meters in some locations. Model 2, with dip 70 degrees, the black dots, which has the largest vertical component of slip, produces run-up comparable to those observed on the west coast, north of just 0.75 degrees. Here, around here. However, the simulations are all well below the observed run-up heights in the rest of the bay. So here we can see 15 landslide source locations that have been identified from existing studies and used for the tsunami inversion. So these pictures are along here. And the column up in the middle represents the simulated maximum tsunami surface elevation in the first 30 minutes following the earthquake, using the results of the preferred tsunami source inversion. And on the right and left-hand panels, we can see images from video footage showing the initiation of tsunami waves along the bay, apparently due to submarine landslides. So here we can see that the largest landslide sources are found between latitudes 0.86 to about just above 0.75 degrees, where the slip is largest in the retrieved finite fault static slip inversions. So this suggests that the landslide generated tsunami run-up has a similar north-south variation along the coast to that of the earthquake source, because strong ground motion focused near the location of the maximum slip was strong enough to generate larger landslides. A sensitivity analysis of the inversion results to the observation locations was also completed. So the right and the left panels show a comparison of the simulated run-up heights with time histories at assumed locations 200 meters farther from the coast, which are the green dots. And it's also good to note here that the simulated run-up heights on the western coast here, have small differences. However, the run-up heights on the eastern coast have some larger differences. And the central panel shows, the central panel shows the maximum water elevation associated with the new inversion. So the contribution of the source is similar to that of the preferred inversion we saw in the last slide, but with greater contributions from a secondary source. But despite these small differences, particular success has to be demonstrated in modeling the video-derived time histories of the surface elevation with a small number of dominant landslide sources. Okay, so when we consider the whole study of Sepulveda, one main conclusion can be found, and that is that coast-seismic deformation played only a minor role in generating the Palu tsunamis, and that several landslides, both coastal and submarine, in Palu Bay were the major contributors to the tsunamis. And if we look back once more at the evolution of the tsunami literature, we can actually see a commonality that has come up quite frequently in most models, and that is that the run-up simulations consistently underpredict observed run-up values. So if we know this, then the question is, what is still missing from these models, if anything? Well, if we look at the absolute ideal model, the absolute ideal tsunami model, the literature shows an interesting pattern. So most of the models use field measurements, and more of this data is becoming available. We also know that 2 tide gauge records are available, which have proven sufficient in quite a few models. But where a lot of complexity seems to lie is in recreating and simulating accurate tsunami arrival times for all 2 or 3 proposed waves. And lastly, many rupture models have already been published, but accurately representing and constraining the fault offshore in particular, especially with lack of bathymetry data, has proven very difficult. So all of these components, in some ways can be done individually, but what makes the most complete, comprehensive model is how well all of these components actually unify. And that is one of the biggest challenges. So in summary, there are a few important things to learn from the Palu tsunami. We know this is a unique event, and in many ways it questions conventional ideas of tsunami hazards related to strike slip earthquakes. Furthermore, tsunami models need to be validated by accurate and available tide gauge and field survey data, which can then be integrated with an accurate rupture model. And lastly, a very key point is that unique tsunamis, such as in Palu, are difficult to provide warning for and need to be incorporated better into regional tsunami hazard analysis. So thank you very much for your time, and I hope you enjoyed this talk.